All right, so we're going to jump straight into chapter 4, and chapter 4 is one of my favorite chapters because we get to start doing actual chemistry. And I want to do a little bit of review. We've got an atom of lithium-6, and how many protons should lithium have? Anybody remember? 3, right? It's atomic number 3, so I'm just going to draw my protons as red dots. How many neutrons should it have if it's lithium-6? 3. So I'll do 3 more neutrons in here. All right, that's going to be my nucleus of lithium, right? How many total electrons does lithium-6 have if it's a neutral atom? 3, okay. And of those 3 electrons that lithium has, how many valence electrons does lithium have? 1, and how do we tell that? Yeah, it's in column 1, right? So what I like to do is say, all right, 2 of the 3 are these core electrons. I'm just going to draw them like that. They're kind of closer to the nucleus in a vague sense. And then we've got 1 electron out here. And like I said, these outer shell electrons are referred to as valence electrons. Most of the time, chemists don't worry about those inner shell electrons because they're not very reactive. They tend to be quite stable. And just to review a little bit, we can really quickly determine the number of valence electrons with an equation. And some of you already spotted the easiest one for neutral atoms. You have to find the main group number. That's the number for the column with the Roman numerals. Let me be more specific. Main group number. And then what you do is you subtract the charge, only if you have a charge. And this gives you the number of valence electrons. So some review. And like I said, if you have a neutral atom, you don't have to include the charge because it's just 0, right? So this is only if needed. All right, so let's do a little bit of practice. Let's do a chart with element in one column. And then we'll do total electrons over here. And then we'll do valence electrons over here. All right, so I'll do magnesium 2+. I'll do chlorine 1-. And then I'll do nitrogen down here. So let's start with magnesium 2+, our first one. How many total electrons does magnesium have when it has a 2+ charge? Yep, it would have 10, right? If we look at magnesium on the periodic table, it's atomic number 12. However, we know we're missing 2 electrons because it has a positive 2 charge, so you subtract 2 from that. That means magnesium would have 10 total electrons. All right, so if you take away 2 electrons, how many valence electrons will it have? 0, right? If we look at magnesium, magnesium's normally in column 2, 2A. If we take away those 2 valence electrons, all of a sudden it has no more valence electrons left. So you can use that as a rough guide. All right, what about chlorine with a -1 charge? How many total electrons will that have? What do you guys think? 18, right? So chlorine's normally atomic number 17, which means when it's neutral, it has 17 electrons. However, it's got a -1 charge, which means it's got 1 extra negative charge. So that means it has 18 total electrons. All right, now the tricky part. Normally, chlorine, when it's neutral, has 7 valence electrons, but we've thrown in 1 extra one, so how many valence? 8. All right, and then nitrogen, just neutral nitrogen, how many total electrons does it have? 7. How many of those are valence electrons? 5, exactly. It's in column 5A. Does that make sense? So things get more negative as you add more electrons to them and more positive as you remove electrons from them. All right. Like I said, we're typically only concerned with valence electrons, and this becomes a big deal with something called Lewis dot structures. So we're going to try working on that for a while. How many of you have heard of Lewis symbols? So some of you might remember from high school chemistry. It's pretty simple though. We represent electrons as dots. Actually, I'm going to clarify this. Represent valence electrons as dots. Around an element symbol. And I'll show you the really basic rules. The rules are straightforward. Only one dot per electron. And then the second rule is add one dot per side of your symbol. Then start pairing. Oh. So I'll show you some examples of this that'll make it a bit more sense. I'm going to just pick a generic non-symbol. So I'll say this is pretend symbol X. And let's say pretend symbol X has 6 total electrons, right? Or 6 valence electrons, I should clarify that. All right, if it has 6 valence electrons, we go 1, 2, 3, 4. So we've hit all 4 sides. And now we need to add 5 and 6. So 5 would go up here, we'd have a paired set, and then 6 would go right there. Does that make sense? Pretty simple rule for drawing a symbol with 6 electrons. So this one has 6 valence electrons. All right, let's do a little bit of practice, and I want you to check with your neighbor and see if you're on the right track. And we'll do Lewis symbols for the following. So the first one we'll do is lithium, then we'll do oxygen, then we'll do magnesium 2+, we'll do my favorite element, carbon, and then we'll do argon. So I'll give you guys a minute to do this, and then check with your neighbor and see if you're agreeing. All right, let's try this as a class. Let's start with lithium. How many valence electrons does neutral lithium have? 1. So that one's pretty simple, right? You just say, all right, elemental symbol for lithium's Li. It has 1 electron. Sometimes students will say, does it matter if it goes on the top, bottom, side? Doesn't matter. You just pick one of the sides and put an electron there. All right, how many valence electrons for oxygen? If we look at the periodic table, it's in group 6A, so 6 electrons. So do I go 1, 2, 3, 4, 5, 6? No, we have to go around each side first. So we go 1, 2, 3, 4, and then the last 2 we do as pairs. So 5, 6. So again, it doesn't really matter the placement. You can have the pairs on opposite sides, the same sides, it doesn't matter. All right, tricky one. Magnesium is normally in group, or it is in group 2A. It normally has 2 valence electrons, but how many does it have with a 2 positive charge? 0. So this one's kind of a trick one. 0 electrons means 0 dots, right? All right, carbon. How many valence electrons does carbon have? 4. So you go 1, 2, 3, 4. You don't pair them. You always start out as single electrons and then pair. All right, argon. How many valence electrons? Whoops. 8. It's in group 8A. So we go 1, 2, 3, 4, 5, 6, 7, and 8. Does that make sense? All right. There's an interesting thing that chemists noticed when they were starting to study electrons and atoms, and that was that elements like argon and neon are incredibly stable. Does anybody remember the name of that column? Noble gases, and they called them noble because they didn't like to react with other things. And they started making some inferences based on that. And this is oftentimes called the Octet Rule or the Octet Preference. So let's kind of describe this. The observation that these chemists made was that noble gases are inert. Does anybody remember what inert means? It just means non-reactive. And they have 8 valence electrons. All right, so they developed a theory based on this, that their stability is due to having 8 electrons. And they called this an octet. And then the deduction that they made was that other atoms want to be like them. So other elements want to gain, lose, or share electrons so that they have an octet. I really dislike the term the Octet Rule. The reality is there's a huge number of exceptions to this, but it works well for the vast majority of organic compounds in particular. And so this is a really good theory for organic chemistry in particular. All right, does that make sense? All right. The next thing we have to talk about before we start building molecules is something referred to as electronegativity. And this was also an observation that they made, was that some atoms and elements really, really want electrons, other ones don't care very much. So for example, this is an electronegativity table, and if you notice in the electronegativity table there's numbers. The higher the number means the more those elements want to steal electrons. The noble gases, if you notice, have no number. So that means that they really don't want electrons. They're happy as is, with the exception of xenon, because it's just a weird atom in general. The rest of them, though, do want to steal electrons. And if you notice, the trend is as you go up towards that right-hand side, specifically towards fluorine, you get more and more electronegative. So the ones in the left-hand corner really aren't that electronegative. So electronegativity is just basically describing how badly an atom wants electrons. So for the next exam, I want you to memorize this table, and then I'm going to quiz you on it. That's a joke. On an exam, if I ask you a question about electronegativity, I would give you this table, or I'll give you some simple tips and tricks. If you notice, the left-hand side is really non-electronegative. The right-hand side is really electronegative. That's really all I want you to know, is that trend going towards the top right-hand corner. And this is important because we have a few different types of bonds. So let's describe this. If you have two elements, and the following apply, we can predict the bond type. Oops, that's a terrible F. If there's a large difference in electronegativity, essentially what happens is the one that's more electronegative is just simply going to steal electrons from the neighboring atom. And I call this a theft of electrons. This is referred to as an ionic bond. We're not going to talk about ionic bonds for a couple of days. We'll eventually get there. Does anybody remember the other type of bond? Covalent, and we'll describe that. That's essentially the opposite when there's not a big difference in electronegativity. And with these types of bonds, they just share electrons. Like somebody said before, this is called a covalent bond. The easiest way to remember the difference between these is when you share something, you cooperate, right? So there's a co in front, meaning that sharing is going on. The other cheesy one that I heard was for ionic bonds. Is anybody a James Bond fan? So they say bond, ionic bond, taken, not shared. So you can use that as a mnemonic to remember ionic versus covalent bonds as well. So we've got two very distinct bond types depending on the difference in electronegativity between two neighboring atoms. We're going to focus a lot on covalent bonds though, and that's what we're going to do tomorrow during our lab. So let's go into a little bit more detail about these covalent bonds where sharing occurs. Like I said, it's a sharing of electrons between two atoms. There must be a small difference in electronegativity. And I like to abbreviate electronegativity EN. Whoops. So small difference in electronegativity, sharing of electron occurs, and it's usually between nonmetals. You don't typically see covalent bonds with metals, at least not in sophomore or freshman level chemistry. All right, does anybody remember where the nonmetals are located on the periodic table? Are they left, middle, right? Not everybody all at once. So nonmetals are always on the right-hand side. So that kind of right-hand corner of the table, that's where all the nonmetals are. So it's pretty easy to spot covalent bonds because they're made up entirely of those. So the groups are 3A to 7A. Like we said, noble gases in group 8A really are happy. They don't want to do anything with anybody else. All right, so let's do some practicing. As you can probably tell, I'm a big history buff. This is chlorine gas, it's Cl2. This was one of the first chemical weapons used in World War I. In fact, we're going through all these anniversaries of these major battles in World War I. Chlorine gas was really nasty stuff. The reality was it wasn't very poisonous, but it made people freak out. And what would happen was they would dump gas on battlefields. Soldiers would jump out of their trench because the chlorine would fill up their trench, and then they would wait for them and then shoot them as they got out of their trenches. It was an awful, awful chemical weapon. So chlorine gas is now outlawed as a weapon due to international treaties, but let's try to draw the Lewis dot structure for it. So we know there's two chlorine atoms, right? So I'll just draw two chlorine symbols side by side. How many valence electrons does chlorine have? 7, right? Okay, so I'll go ahead and I'll say 1, 2, 3, 4, 5, 6, 7, right? We'll do the same thing on the other one. 1, 2, 3, 4, 5, 6, 7. If we look at each of those chlorines, though, they're not happy because they don't have an octet. So what they'll do is they'll just share electrons in order to have a complete octet. And in particular, they like to share electrons that aren't already paired. So I'll kind of circle those up and say those are unpaired. They can maybe share those. So what we'll do is redraw this. And when they share those electrons, they now have a pair sandwiched in between them. Looks like this. And we've got these electrons, shared on the outside. I'll circle those in green. And then we've got another type of electrons that are shared in the middle. The ones in between two atoms are called bonding electrons. They're the electrons that are shared in between two electrons. And then the electrons that aren't shared, the ones more on the outside, those are called lone pairs. Oftentimes what people do is instead of showing bonding electrons as dots, they'll just represent them as a bond line. So I'll show you what that looks like. So for example, with chlorine, Cl2, you can draw Cl, straight line to another Cl, but you do want to show those lone pair electrons as individual dots. So can show bonding pairs as a line. Does that make sense? So now each chlorine has 8 total electrons around it. You get to count both of the shared electrons anytime you're sharing them. All right, want to try a hard one? I'll give you guys some time to think about this. We're going to do a bunch of this tomorrow, so don't panic if it seems unnatural at first. Let's do NH3. This is ammonia. It's a precursor to making fertilizer. Or actually, it's just sprayed on some fields as fertilizer. So what I want you to do is to figure out how you can link these together. And I'll get you started. We've got 1 nitrogen, and we've got 3 hydrogens, right? We've got a 3 after the H. So whenever I do this, I like to space my hydrogens around kind of like this. So I'll give you guys a minute to see if you can figure out how it's linked together, and then check with your neighbor. All right, let's try this as a class. Let's do the easy ones first. Hydrogen, how many valence electrons? 1. All right, so I'm just going to go 1, 1, 1. I like to have the electrons facing each other because we know eventually we probably want to bond those. All right, how many for nitrogen? 5. So I'll go 1, 2, 3, 4, 5. Nitrogen's not happy. It doesn't have an octet. However, maybe it can share electrons with this adjacent hydrogen, and this one, and this one. Remember how I said I don't like the term Octet Rule? Hydrogen, in this example, is fine not having 8 electrons. So hydrogen's kind of the one major exception to this rule. So now let's redraw this using that bond line notation. So we've got nitrogen sharing electrons with hydrogens. So that line represents a shared pair of electrons. Same thing with this hydrogen. Same thing with this hydrogen. And am I done? No. We need to draw that lone pair on the top. So 2 electrons for the lone pair. So this would be the correct Lewis structure for ammonia. We do have to remember those lone pairs, and we'll see why tomorrow. It actually influences their shape. All right, let's try another one. We'll do a few easy ones, and then we'll jump into more challenging ones again. We'll do CH4. The simplest organic molecule. This is methane found in natural gas. So one nice thing with carbon is carbon always wants to be in the center of things. So when I go ahead and I plan my Lewis structures, I know I've got carbon smack dab in the center. The hydrogens, I'm just going to evenly space around that carbon like this. We know hydrogens have one valence electron, so I'll put one dot next to each of them. How many for carbon? 4. So I'll go 1, 2, 3, 4. All right. Same thing. We want to pair these up. So now carbon's got 2, 4, 6, 8 electrons, and all those electrons are paired. So now if we go ahead and we draw this as a bond line notation, we can say, all right, carbon's going to be smack in the center. We've got bonds to each of these hydrogens. This is how most chemists and biologists draw out compounds. They really like to draw the lines rather than dots. It looks kind of cluttered with dots, but you're welcome to draw it either way. Does that make sense? So if you notice, all of these bonds that we've been showing are what we call single bonds. So we're sharing a single set of electrons. However, some molecules actually have more than one bond between them. These are called multiple covalent bonds. Some atoms share more than one electron. And I'll show you an example of this. Makes more sense with an example. Oxygen gas, or O2, the air we breathe in. It's made up of 2 oxygen atoms. So I'll draw those 2 oxygen atoms side by side. How many valence electrons for each of them? 6, right? It's in column 6A. So I'll go 1, 2, 3, 4, 5, 6. Same thing with this one. 1, 2, 3, 4, 5, 6, like that. So they're side by side. Each of the oxygens doesn't have an octet. Easy thing to do is say, hey, we can share these. However, the oxygens, if you look, we've got 2 electrons here. That's 2, 4, got 6 because of that shared one. We still only have 7, right? So what do you think we might want to do? Yeah, we could share the bottom too, like this, right? Okay, so if we go ahead and we draw this, same idea, say oxygen, we've now got 2 bonding sets of electrons linking them both up. And then we've got 2 lone pairs off of each oxygen, right? So if you have 2 lone pairs, you can say like that or that. Oftentimes you try to draw them relatively evenly spaced around the atom, so you don't have to have them side by side. Does that make sense? All right, let's try a hard one now. Does anybody know what the air we breathe is mostly made up of? It's not oxygen. Nitrogen. Nitrogen is N2. So let's go ahead, draw those 2 nitrogen atoms. And I want you to see if you can figure out how to link these up together and then check with your neighbor. All right, and give me a thumbs up if you think you got it. All right, so we've got 5 valence electrons around each nitrogen, right? So I'm going to arrange them like this on purpose. I like having the lone pairs kind of pointed out and away. It makes it easier to link up the unpaired electrons. So really easily we can say these 2 are going to be paired. Oh, we can pair these 2. Then we can pair those 2. So if we redraw nitrogen, we can say there's a triple bond in between with a lone pair remaining on each nitrogen. So this one's a triple bond. And then up here we had a double bond. Which one do you think is stronger? Triple bond, exactly. The more electrons you share, the stronger the attraction is going to be between those atoms. All right? I was told on one of my surveys that I was quite morbid, but it was enjoyable, so I'll do another war gas. Do COCl2. This is another World War I war gas. As they went through the war, they actually found better ways of creating chemical weapons. This was one of the more poisonous ones. So chlorine was the first one. Didn't work very well. Just scared people, made them jump out of their trench. Phosgene, on the other hand, when you breathe it in, will actually react with the mucous membrane in your lungs and start creating acid. So you can imagine if you're forming acid in your lungs, That's not good. So this one was far more toxic, and it's referred to as Phosgene. Phosgene today is primarily used for making a huge variety of plastics. So it is still used in the chemical industry, but you have to be very careful working with it, obviously. All right, like I said, carbon likes to be smack dab in the center, so let's see if we can figure this one out. Okay, so let's try this super quick. Like I said, carbon is unique. It always likes to be the backbone or center molecule. So we've got one carbon. We've got one oxygen, so I'll just put it kind of wherever I want nearby. We've got two chlorines, so I'll say, all right, chlorine here, chlorine here. How many valence electrons for the chlorine? 7. So I'll say 1, 2, 3, 4, 5, 6, 7. Like I said, I like my unpaired electrons to be facing other atoms so we can link them up easier. We'll do that. All right, how many for oxygen? 6. We'll go 1, 2, 3, 4, 5, 6. And then if we think about carbon, right? Carbon should have 4. So we'll say 1, 2, 3, 4. Let's start with oxygen and try to link it up with the carbon. So we know we can definitely pair one of these sets, right? But we also need a second set to pair so that the oxygen has an octet. So it looks like carbon and oxygen can form a double bond, right? All right, we still need to link up the chlorines. So maybe these electrons can bond together, and then these electrons can bond together. Okay, so what we do is when we want to redraw this, we say carbon has 2 bonding sets with oxygen. The oxygen still has 2 lone pairs left over, so I want to include those lone pairs. We've got a bond to chlorine on each side, and the chlorine, each of them has 3 lone pair sets. Sometimes students will ask me, well, why did you draw it that way instead of this way? And I'll show you why. And we're going to talk about this more tomorrow. We won't have enough time today. But atoms don't like to crowd one another. They like to spread out and not be super close. So for example, if we look at this one up here, this prefers to be approximately 120 degrees apart versus over here, this one's 180 and about 90 degrees. It would prefer to be evenly spaced all around. It's kind of like awkwardly standing close to somebody in the hallway. There's this comfortable distance you want to be from other people. So it's more appropriate to try to show them evenly spaced around that central atom. Does that make sense? All right, so like I said, try to start working on your pod soon. Tomorrow we're going to probably incorporate a little bit of lecture into our lab activity.